sound for Colin to take over. And Colin will talk about self-organizing wetland bioreactors, application to mining on the moon, direct and indirect bioremediation of regolith slurry as a design call for mine-influenced water benefaction. Colin has been building and investigating self-organization in open and semi-enclosed ecological systems for 15 years and seems to be pretty successful at that. So the floor is yours, Colin.
Yeah, pretty successful. I mean, only time will tell. Is the audio good?
Audio is fine.
Okay, excellent. Thank you. Share. Okay, quick shout out then to Frida and Doug and Nick. Great to have you guys on board. Thank you very much. I met Doug through the Mars Society. I met Frida through, and as well as Nick Mellis through the Mars Society, and Frida through the Spring Institute, and then she's been coming to our Ecology X meetings. And is the slide presentation visible?
And the presentation is looking good. Yes.
Awesome. Okay, great. Yeah, I'm going to try for about 20 minutes here, and then a couple questions. Yeah, so slideshow. Okay, so I build self-organizing wetland bioreactors called SOWBs. I patented them back in 2013, but patents are a you-know-what show, and they're really only as good as your attorneys, ultimately, and your ability to then produce, manufacture, sell, and continue to market. So we are technically at a TRL, or technology readiness level, of, between 8.5 and 9. I've been building them since 2012, so 12 years. We originally started in hydroponic growth, floating growth mats called floating islands. And I went to Penn State, and my dad was a professor of microbiology and genetics, and he was the one who turned me on to Winogradsky columns. Now, unfortunately, he passed in 2017, so I've kind of picked up the baton and have been running with it ever since. So my primary line of work is in acid mine drainage remediation. So I don't really work with the mining portion of it. I work with the pollutants after the fact. So you've got impacted water, or mining influenced waters. That's apparently the term that they prefer to use nowadays, because it's not an impact. And that makes sense when some of the dissolved ions in the water that have been influenced through acid mine drainage remediation are valuable, like rare earths, manganese. There's a lot of sulfides that are broken down, dissolved within a regolith pile, you could say. So, taking mining equivalents and putting them on Luna and on Mars. Now, originally this presentation had been written for Mars, but it works here on Earth, and we're expecting it's going to work on Luna and Mars, because this is this is the way that wetlands work. So the first portion of this talk is going to be, what the hell is a wetland, and what's a bioreactor, and why do I care? Okay, so what is a wetland? And this is a presentation that's built around the fact that engineers don't generally have much in the way of biology. So I'm going real basic on some of this stuff, but it's going to go pretty heavy here fast. Okay, so what is a wetland? It's got water, holds water most of the time. Water moves through it. There's an influent and an effluent. There's a high surface area to volume due to plant life. It's got high biomass to volume due to the plant life and the microbiology and all the other critters, as mentioned and asked before in the last couple questions, nematodes, all three of the kingdoms of microbiology, and you begin to see stratification and the like, and we'll talk more about that. But cycles matter and energy, lots of ways, both biotic and abiotically. And most importantly, it's self-organizing by Gibbs-free energy and the prevailing atmosphere. Now, Gibbs-free energy is the amount of energy that any metabolic triplet will gain from, the amount, and you can factor it as the amount of ATP, or acetyl or adenosine triphosphate, NADH. So, the amount of electrons transferred through a system. The more electrons transferred, the more energy in every one of those metabolic triplets, and which gives them then a competitive advantage to growth and reproduction, meaning they go first. and then they use up all the material. And then the next thing comes along, and it uses up all that material, and on and on. And oxygen's the first thing that goes. Dissolved oxygen. The O2, dissolved in water. Okay, and then what's a bioreactor? It does predictable and reproducible work. When I say work, I mean that in the classical sense of energy in, energy out, some kind of a product, whatever that should be. And basically then a bioreactor is a biological engine ruled by the laws of conservation of mass and energy. Makes sense, generally speaking. Catalyzes reactions, producing useful byproducts. And this is where it's BISRU, biological in situ resource utilization, not just ISRU. So you're not just using thermal, mechanical, electrical, nuclear forces. You're using all those, yes. Plus you're catalyzing them with the biological / ecological components that are working for peanuts. They do it for free, which means a system that is based off of SOWBs is basically doing 90% of all the work for you in benefacting, isolating different products throughout this system. Now a natural wetland. And by the way, that's San Francisco in the background there. I took that from last place my sister was living, if you're kind of curious. I took all these pictures myself for the most part. It's a beautiful day there. You can see the bay, the Golden Gate's off there in the distance, and there's the Bay Bridge, and you can see San Francisco. There's the Coit Tower, I think you can see. Anyway, it used to be a tour guide in San Fran. It's a beautiful place. But natural wetlands, which if you look hard enough are actually in that picture, are self-selecting and organizing, and that's called EPA. Calls that, or the Environmental Protection Agency calls that natural attenuation. So that's another term for it. And by attenuation, that's, basically if you think about a rock at the top of the hill, and that would be certain metabolites going through a biological process and then using up that energy source. So you're rolling the rock down to the bottom of the hill. So the difference between potential going to kinetic back to potential energy until it's at the bottom of the hill and can't roll any further. So a natural wetland is always going from the most energetic to the least energetic. Once again, law of conservation of energy and mass. Now, constructed or manufactured wetlands. So constructed wetlands are for like acid mine drainage remediation, whereas a manufactured wetland is what I build. Those are the SOWBs. It's a wetland in a box. It's the most simplest way. I can walk down the street here in Altoona, walk into the bar and, tell somebody, oh, what do you do? It's like, I build wetlands in a box. Oh, okay, that makes sense to them even. So if anybody asks, that's what I do. But with a manufacturer constructed wetland, you know that you've got an influence that you know something about, and you need to do something with it because it is considered a pollutant if it gets off of your mine drainage site. So EPA regulates the amount of material that can get off of that site legally. And you got to catch everything else in between there. And you have to do that through a number of means, both biological and abiotic. That's what a constructed wetland does. And then they're much larger and usually very inefficient. And you don't have an opportunity to reclaim the materials because you're not separating them. You get this big heterogeneous muck from a heterogeneous dissolved load that's in the water. Okay, so bioreactors specific and by definition, natural wetlands, methane digesters, which we now are starting to build, reclamation ponds, that's that constructed wetland, fish tanks. This goes back to Dr. Taub's work, Frida's work. She does some great stuff. People, please check out some of her work. It would answer a lot of your questions. Greenhouses, of course, because you're there's still a wetland component. It is the soil. There's water in it. You've got a load. You've got living biology in it. So once again, stretching a little bit, but it's still a bioreactor. It's producing work and there's water in it. Now, whether it's a estuary or a cornfield, the amount of water changes. The product or the purpose is the same, though. Waste treatment plants. Wine and beer vats, although technically they would be batch reactors, not flow-through reactors. And you can even extend it. People, plants, box turtles, and my dog River. Picture there. She doesn't see that box turtle. She's a bit of a strange golden retriever. Okay, so oxidation reduction potential. That's screwing with my time here. So redox then is the vacillation of and the movement of electrons, both biotically and abiotically. ATP going to NADH in aerobic metabolism. That's redox. Not to continue to get too deep into it because I'm not a biologist. I'm, an ecologist on a good day. That would have been one for Dad. But the purpose here is to see this. So you got this thing called a redox ladder. You have the most energetic metabolites and triplets at the top. That's the oxic, the O2, and then the least efficient, those that produce the least amount of ATP down at the bottom, which is carbon dioxide reduction to methane. Pretty useful substance, especially if you can get the sulfur out. So each one of these steps going from 32 ATP for the O2 down to methane for the 4. What this does is it tells you, based off of the efficiency of the reaction, which one comes first in an open system. And by the way, that these are being catalyzed by different forms of metabolism, whether it be, we're using carbon dioxide and say, for the autotrophs or for the phototrophs, plants. But there are microbes like chemolithoautotrophs, like manganese oxidizing microbes that then produce manganese oxides. There's a whole bunch of different kinds of metabolisms, but the things that you always want to remember is like, what's the carbon source? What's the energy source? What's the oxidizing gas? You get those 3 and you put them into a chart and you know what you're looking at, and you can then make predictable implications on what is coming out next, depending on what is in that heterogeneous load. So it's a way to then separate the load depending on the different metabolites within that system. And you know that it's predictably, you've been given a roadmap. It's what you're looking at right here in the redox ladder. And then you can just go down through your steps. And this is, in general, the Winogradsky principles. Sergei Winogradsky, who was a Ukrainian scientist, back then it was Russia, but it's Ukraine now. It worked out of Kiev, and he was the first one to do a lot of the elucidation on sulfur and nitrogen species and changes, and the stratification using Winogradsky columns, which is just a glass column that then vertically stratifies, because you've got an open atmosphere of oxygen at the top, and then you've got a sulfidic or a methanic system at the bottom. And then as the oxygen is able to percolate and diffuse as it dissolves down through the column, it makes those zones. And it's something that is visually represented. You can go ahead and look it up on online. Just look up Winogradsky column. What I'm building is essentially just a very, very, very large version of that, but just on its side. So you get individual pockets that you can draw off gases. Let's see. So it can also be measured then, and this is kind of the cool thing about it. Like, it can be measured in millivolts. So if you've got an ORP probe, which would cost you about $30 online, and it's essentially just an electrical tester, and it's in millivolts. Our biology is essentially, as aerobic biology down to the methanic biology, is about 0.9 volts. It's literally a battery. If you think of it that way, it's a really easy way to approach the process. And then if you were to also add wires to it, essentially you can short circuit it and pull electricity off of it. And I'm going really slow. But it's been used as a teaching tool in biology classes, microbiology classes for 100 years, but nobody's ever figured out how to properly apply it. That's where we got the patents. Let's see. So, and for the engineers in the room, so in this context, and application, SOWBs are multi-fuel and multi-oxidant biological engines that self-organize to use each reductant and oxidizer sequentially based on the energy released and the availability of the metabolic pathways. Metabolites can be skipped over if the genetics aren't present. And once again, on Earth, we have ubiquitous biofilm. These critters are everywhere. They've been aiding in the turnover geochemically for, well, as long as there's been biology on the planet, which, so about 4 billion years, give or take. But a long, long time. We have way more minerals on Earth here than there are on the moon, in part because of the biology that is able to affect them. Trophism, I'm not going to really get into this one. But everybody, I think, understands that you got a 10% energy transfer from top to bottom. And so primary producers or deep sea vents are the the primaries and are acting independently all the way to us. Or in this case, the third level, second level consumers. The farther that we can feed the Lunites on the moon there, the farther down the trophism scale, the less energy it takes overall, but nobody wants to eat only rabbit food. So that's where we got to get back to growing the worms, as just previously mentioned. By the way, it was a great last talk there. That was a wonderful talk. And then feeding it to the chickens or the fish, and then all these other components come into the systems. But the great cycler is the wetlands. That's the thing that everything comes back through, whether it be the regolith coming in one side or the habitats coming in the other, combining those two and allowing them to precipitate out those individual components and what is basically a large biochemical production system that allows for the benefaction and drawing off of those individual chemicals. One thing that I'd seen yesterday that I did not know is there is practically no nitrogen. To that presenter, I thank you. That was a big one, because if you go back up to the redox ladder, aerobes, denitrifiers. Roadblock right off the bat. Absolutely right. We're going to have to get ammonia up there in one way or the other. It also says that you're not going to be using ammonia for any kind of fuel. Why would you waste it? There's methane. So just in the long-term implications are how you're getting back up off of the 1.6 gravity. Okay, so these are some of the units that I've built. This system was actually just rebuilt by another group, which I'm a little bit bummed about, but now we have these for methane digesters. We just weren't quite hitting our numbers on manganese. It's business. It's what it is. Let's see. So in this case, we were attempting to pull the manganese, which is the M2 in solution, Mn2 in solution, which is the terminal electron donor. CO2 is the carbon source there, so that makes it autotrophic. And O2 is the exhausting gas because it is an aerobic system. So it's a chemoliteral autotrophic system. Once again, and I have to put together this chart one of these days of all the different metabolisms, because then they would factor into that redox ladder. Here's another system that I built in Philadelphia area, Kennett Square, removing BOD, TSS, fecal coliforms, iron, manganese. I think we were also testing for potassium and phosphorus there. And we were getting some pretty good numbers, usually about 10 to 1, where we were pulling about 90%. Those are 4 reactors. That's about 3,000 gallons of total capacity, running at about 40 gallons a minute. And then all the sludge that we were collecting in the systems went to dewatering bags. So the water was a pass-through system, and this is the front end for a reverse osmosis machine. But we got killed with oil and grease because upstream they just wouldn't separate the materials when they had an opportunity. So it became a management, not a technology issue. Once again, this is business. You learn, you build better, and you grow. And by the way, these last couple slides here, I do not build these units anymore. We've got a new means of manufacturing using culvert pipes that are 5 times the volume and only twice the cost, which really starts bringing us in within the range of our competition in mining, but not just, and that's for cost. We've already got them beat by size by a factor of 2 exponents, and also in the capability of being able to get benefaction. So you pull all your iron first, then your manganese. If you go reductive, then you can pull your sulfur, which would drive off hydrogen sulfide, could potentially be captured for sulfuric acid, but then that's also an alkalinity adjustment, while also reducing your suspended or your electroconductivity, which then when reoxidized means that you've got a pH balance where the metals have the correct kinetics where they actually start to oxidize and fall out at lower rates in general than are necessary through standard pH adjustments, through the use of caustic soda or slaked lime or, those kind of the really classic mine drainage amendments. That's my dog. Once again, that's River Bear. And that system right there, that is, well, obviously, I built a space toilet. Never did get to test that one, though. Ran out of funding, because when you're a business, you got to pay the bills, and R&D is just as tough for everybody else as it is for a business. But those systems would again be based off of the Kennett Square system: BOD, TSS, fecal coliforms, nutrients, driving off what gases you can. That smaller box is a 2-chamber unit, about 78 gallons. The one up at the top there is about 200 gallons. And that's sitting in my new shop to be finished now that we just recently won a grant from the American Recovery Act plan. Thanks, Joe. And got a shop down locally where I can build these new massive reactors of 2,500 gallons. So a scale that's actually worthwhile. So that's manganese oxide, it's either ranciaite or bernacite. I forget which. It's 85% purity. We grew that in our reactors at a mine drainage site. And it also has about 2 to 3% strontium. And I have had a difficult time. So in some sites, I can get it to work like gangbusters. In other sites, I couldn't get it to take hold. Still trying to figure out what the specific niche is for that system. And I mean, we were getting manganese out in here. We just weren't hitting our numbers of less than 2 milligrams per liter. And it was mostly in the cold. It was fine all the rest of the time of year, but once it gets below 50 degrees, you get all the iron out. In the presence of strontium, it should have gone like gangbusters. There's still more to learn. Metagenomics might help out, and we did determine that was XRD and what was the other one? SEM. We were able to determine what it was. Okay, Gaia machine learning. So in a larger system, my friend and coworker Briar Fisk is the developer for the Gaia module, which is the operating system for a spaceship ecology, essentially based off of SOWBs. Let's see, to the plant people, I'm running out of time here. Yeah, we can. Okay, so this is the biggie. This is you can see top right or top left there and everything in pink, that's regolith. Everything in green, the 4A, 4B, 4C, that's your habitats. 4D and 4E are your manufacturing and the like. And all the blue stuff in the middle, that's all your Winogradsky column style. That's your self-organizing wetland bioreactors. That is the hinge. That's a keystone between both of those sections. Now, this one in particular was designed for Mars and was entered as part of a Mars Society competition a while ago. If anybody's going to be around later on for James Burke, he'll be on. I think I got that name right. And this has perchlorate in it. So how salts work, how your metals and your metalloids can be impacted by microbiology. And once again, this is using all three kingdoms. And this is one of those deals, forest for the trees. Don't get stuck on the trees. Look at the forest, big picture. Every one of these, I was here all yesterday listening to everything, and every one of those talks yesterday, for the most part, could be put into 4A, 4B, 4C, or somewhere in 1A, 1B, 1C. There was some talk about the comminution so you got 2A, 2B, and 2C was also factored in, but nobody's talking about wetlands, because that is the thing that'll do 90% of the work for peanuts. Yeah, cool. Thanks. Ben Franklin Tech Partners, thank you. Everybody in Arcology X, Stuart, Frank, Breyer, Dr. Dan Tompkins, S.J. Parsons, Mars Society, Stelly, Pat Grubbs for the Spring Institute. Thank you for Frida showing today. And of course, Doug, glad you finally got to sit on one of these. And hi to Nick. Okay, I got 5 minutes for questions.
Yep, we have one in the chat.
Stop share.
Or a comment, probably. Fuel needs oxygen to burn. We want solar or nuclear. I don't agree with nuclear personally, but yeah. Yes, it most certainly does. And the processing of the regolith will certainly provide plenty. And once again, I'm not a there's a camera. I'm not a geologist, but having gone through watched some of the other proposals, that I don't think oxygen's going to be an issue, and that I would then propose production of the methane for getting back off the surface is probably the easiest way to do it, because once again, if you just let what carbon you have within those systems, they'll eventually be reduced to CH4. Yeah.
Chart. What does 4A 3H mean? Thanks. Oh yeah, and my apologies. Like, it's a super busy slide. This is a big no-no. Let me go back to that one. Reshare just real quick if I can find. Let's see. It's 4A and 3H.
Gary Barnard.
Okay. Okay. Are we reshared there, Nicholas?
Sorry. Yeah, you sure. Yeah.
Yeah. Oh, 4A is a civilian habitat, so it's 25. So I mean, basically, these are your haves. This is where all the people are going to be living, and they're going to be respiring. Waste is going to be coming off of that. And anybody can, if you want to see this, please. This is common source. It's open. Please email me. I'm happy to send it to you. Punch holes in it. It's cool. This has never been peer reviewed. Nobody's ever even tried to peer review it, to be perfectly honest, because it's a big picture kind of a thing. So I do welcome anybody punching holes in it. It's like my ego's not so big that I can't take that. Let's see, it was 3H was a sulfate reduction. So this is where 3H plus then is the production of sulfuric acid, which you would use for continued acid leaching. So if you think about here on Earth, most of our copper is coming from the acid heap leach process, where you dig a whole bunch of material out of the ground and you just pour sulfuric acid on top of it, and solubilizing those ions such that you can then do a pH adjustment later on down the line and precipitate and flocculate and then froth and drive off the copper. And that's how we get most of it today. So it's not like you're pulling out copper in big metal chunks. It's you're dissolving it all the way down to ions. That's essentially also acid mine drainage. Now, as mentioned earlier, rare earth elements are in our acid mine drainage. It is proposed that up to 3 times our total requirements here in the U.S. of rare earth elements come out in our AMD every single year. We're just not collecting it at all. Now, there's DOE, DOD has been spending a lot of money on those processes, and this could be a component of it at some point. Let me just unshare again.
Gary Bernard has my question, has raised in hands for a while.
Yeah.
So,
Colin, again, an excellent presentation.
Hey, Gary, good to see you again. Yeah.
Curiously enough, in the early 80s, there's a study out of the University of Maryland that was looking at methane digesters in a space environment. It turns out that the crossover point was 6 astronauts in terms of being able to generate useful amounts of methane for propulsion purposes. Okay, it occurs to me that in looking at your generalized flow and process diagram there, that there's essentially some form of quantitative or scaling metric that could be associated with each one of those. Have you looked into that, or is that part of your business processing planning, or what's your feel for how you take the analytics and turn that into what's the product volumetrics at each stage?
Yeah, I'm going to need a lot better scientist or a chemist or a biochemist than I am. My job is to look at the systems, see what the products are based off of those redox pathways. So that's a great question, because what you're asking is, like, as mentioned, if it's 6 to 1, it gives you enough juice to get off the ground. But then is that coming from their poo, or is that coming from a plant hab? What about the non-edible food products, corn stalks, silage, and the like that we couldn't eat but would go to something else? So there's a lot more that goes into it, which is it's a great question. I don't have a good answer for you yet. Those are just the steps, and then what the products, what the stoichiometry and the mass balance is after that takes another person who's a lot better at the chemistry than I am, because I wouldn't necessarily trust my own personal numbers. So that's looking for others to help with that. Great question. Wish I had a good answer for you. I'm mostly just the 10,000 foot, this is the pathways, but then depending on what the inputs are will depend on what the outputs are, kind of a deal. It sounds a bit like a cop-out. I do apologize. But
it's not a cop-out. What I'm pointing out is that diagram you've got. If you start with an outcome, basically you say, okay, what can be the outcome of this? The set of folks that have some entree into the middle ground there to help out and refine the calculations, it becomes much more accessible.
We have to cut there. Unfortunately, there is also Frida wanting to cut in. So that's we might be able to resume that in the panel later. However,